It began with a number that refused to make sense. 3I/ATLAS, the third interstellar visitor ever recorded, was not behaving like any comet before it. Instead of accelerating as the sun's gravity drew it inward, its motion seemed to ease. For weeks, astronomers tracked its light curve expecting a steady rise, a slow burn powered by geometry and sunlight. What they saw instead was a surge 5 times brighter than predictions, a jump too steep to be explained by distance alone. The anomaly stretched across 4 weeks. Telescopes on different continents using different instruments recorded the same pattern. Night after night, the object glowed stronger, climbing in brightness faster than any model allowed. If it were a typical comet, jets of gas should have nudged the nucleus off its course, pushing it slightly faster, bending the orbit in measurable ways. But Atlas refused. Its light surged, yet its path hardly shifted. That contradiction set the stage for one of the most provocative debates in modern astronomy. Some framed it as runaway outgassing. Maybe Atlas had exposed patches of exotic ice, pockets that ignited suddenly as sunlight reached them, releasing vast amounts of material in a short time. Others were less certain. The brightness curve was smooth, persistent, without the jagged spikes of a volatile-driven eruption. A steady increase like this looked different, almost deliberate. Whispered on forums and in quiet side channels, a question emerged. What if this was a maneuver? What if ATLAS was not just a comet, but something guided? The mystery deepened when spectrographs began peeling back the glow. Observatories in Chile, Hawaii, and Europe pointed their instruments toward the coma, slicing its light into spectra. The expectation was simple. Comets in the solar system always reveal a familiar mix of volatiles, dust, and metals. Among those metals, nickel and iron march together. Forged in supernova, they are cosmic twins, liberated side by side whenever sunlight heats a comet's crust. Yet Atlas broke that rule. The data showed nickel in abundance, streaming off the nucleus at measurable rates. But iron was missing. Even after nights of cross-checks, calibration sweeps, and comparisons with field stars, the lines for iron refused to appear. The ratio was skewed far beyond anything in the local catalog. In some models, nickel outweighed iron by as much as 50-1. No comet in recorded history had ever produced such a ledger. Theories rushed to fill the void. Perhaps exotic fractionation during formation had left ATLAS with a unique chemical fingerprint. Maybe selective sputtering, the stripping of atoms by cosmic rays, had eaten away at iron over billions of years in interstellar space. Or perhaps unusual weathering had reshaped its crust in ways unseen in our solar system. Each explanation carried weight, but none felt complete. Against the background of doubt, a more speculative idea surfaced. What if this was not natural chemistry? What if the nickel came from engineered alloys, the kind forged in furnaces, not born in clouds of dust? The idea was radical, but the numbers made it hard to dismiss. Nickel-rich superalloys are prized for their strength and resilience, used in human spacecraft to withstand radiation and heat. To see a signature like that in the coma of an interstellar visitor was unsettling. Astronomers cautioned against leaping to conclusions, but the whispers grew louder. Maybe the chemistry of ATLAS was not entirely cosmic chance. If the composition was strange, the motion was stranger still. For comets, jets of gas act like thrusters. Each outburst pushes the nucleus, changing its speed or tilt in ways that can be measured precisely. The effect is so reliable that astronomers build it into orbital models, predicting the tiny accelerations that come with each new jet. Borisov, the interstellar comet of 2019, drifted by nearly 100 kilometers per day as its outgassing shifted its orbit. Even Oumuamua, the shard-like object of 2017, veered tens of thousands of kilometers without any visible coma at all. Atlas should have been no different. Instead, its drift was almost invisible. The numbers showed only 1 to 1.5 kilometers per day, far below expectations. The coma stretched for hundreds of thousands of kilometers. Dust streamed in images, yet the orbit remained almost perfectly gravitational. Models that accounted for its visible activity predicted a much larger deviation, but the trajectory stayed locked, pure, resistant to the forces acting upon it. That left 2 unsettling possibilities. Either Atlas carried an immense hidden mass, dense enough that even strong jets barely moved it, or something was actively correcting its course. The first option strained credibility. Photometry placed strict limits on the size of the nucleus, and nothing in the data supported a mountain of implausible weight. The second option was even harder to voice, that ATLAS was stabilizing itself, using control to stay on track. The paradox gnawed at astronomers. Every update from observatories tightened the error bars, and still the drift refused to rise. It was as if the object were immune to its own activity, venting gas without consequence, glowing brighter without altering its line through the solar system. The contradiction between what was seen and what was measured made ATLAS the most enigmatic interstellar object yet. And so, the conversation turned to SETI, the search for extraterrestrial intelligence. For decades, the hunt had focused on radio signals, laser flashes, and faint beacons hidden in the static of the cosmos. The assumption was simple: civilizations broadcast, and we just needed to tune in. But Atlas suggested a different approach. What if the best evidence was not something we heard, but something we saw? A macroscopic technosignature, a physical artifact drifting between stars, could endure for millions of years. Unlike a radio signal that fades, an object could carry information, technology, or intent long after its creators were gone. It could be studied, measured, even intercepted, a tangible relic rather than a fleeting whisper. The discovery of Oumuamua had cracked the door on that idea. The arrival of Borisov pushed it wider. With ATLAS, the concept surged into the mainstream. The Comet, or whatever it was, became a candidate not for what it transmitted, but for what it embodied. Its glow, its chemistry, its refusal to drift in expected ways all spoke in a language of anomalies. If SETI's mission was to search for signs of intelligence, then Atlas presented itself as a message written not in radio waves, but in physics, motion, and light. The trail of 3I/TLAS did not begin with a sudden announcement. It began quietly, hidden in the background noise of the cosmos. On May 7, 2025, the Transiting Exoplanet Survey Satellite, TESS, recorded faint smudges of light against the crowded backdrop of the galactic center. At the time, it looked like nothing more than clutter, a fast-moving dot lost in the star fields. No alarms were raised. The object swept onward, night after night, stacking trace after trace into hard drives no one was checking. For weeks, it remained invisible, a ghost in the archive. It was not until July that ATLAS, the survey that gives the comet its name, flagged an anomaly. By then, the object had surged 5 times brighter than when TESS first caught it. The data did not fit any known trend. Almost instantly, observatories pivoted. The Minor Planet Center logged the new arrival, and telescopes worldwide turned their instruments toward the coordinates. Suddenly, what had been a buried line in the background was a global event. As word spread, other surveys went back to their own data. The Zwicky Transient Facility found pre-discovery frames from late June. Pan-STARRS in Hawaii turned up additional traces, filling in the path. Amateurs joined in, combing through publicly available archives, turning up faint trails from mid-June that added more detail to the light curve. Piece by piece, the puzzle came together. What had looked like an isolated flash was actually a steady, persistent brightening that stretched back weeks before the official announcement. The timeline revealed more than just a detection. It revealed behavior. At distances where water ice should remain locked and inert, ATLAS was already shedding dust. The coma was visible, the cross-section growing larger with each passing day. The numbers could not be dismissed as chance or error. Multiple instruments, multiple continents, all told the same story. Atlas was active earlier than any comet had a right to. And if you're following this unfolding mystery with us, make sure to hit that subscribe button and drop a like so you never miss the next update on Atlas's journey. As the professionals built models, the amateurs built timelines. Across continents, backyard observatories pointed their telescopes upward. Small frames, faint streaks, shaky exposures, when stitched together, they told a story that no single survey could have captured alone. Global forums became the backbone of this effort. Discord servers, Telegram groups, and astronomy boards lit up with data sharing. Someone in Australia would capture a faint image at dawn. Hours later, someone in Spain would confirm the same surge. Within a day, a network of amateurs had created a timeline as robust as anything from professional observatories. This collaboration changed the game. Early warnings spread across continents in real time. A sudden flare spotted in South America could trigger a response in Asia the same night. Larger telescopes, alerted by these networks, used their scarce observation slots more effectively. What once required weeks of coordination now happened in hours. The gap between professional and amateur blurred. For Atlas, every frame mattered, and together the world was watching. It was a reminder of how astronomy has evolved. Telescopes no longer work in isolation. They are linked by fiber optics and by forums, by communities that stretch across time zones and languages. The discovery of Atlas was not just a triumph of science, but of participation, a global act of seeing. For many, the object was the first interstellar visitor they had tracked with their own eyes, their own equipment. That connection gave the data a weight no algorithm could replace. With each update, the contradictions grew sharper. This was not just another visitor. It refused to behave like any comet on record. To see that, all anyone had to do was look at the lineage of interstellar objects. In 2017 came Oumuamua, the cigar-shaped shard that raced through the solar system with no coma, no dust, and yet inexplicable acceleration. 2 years later came Borisov, the opposite, a comet by every measure, complete with a bright coma, blue ion tail, and measurable non-gravitational drift. Then came Atlas, a third chapter that broke the pattern again. Unlike Oumuamua, ATLAS carried a coma that dwarfed Jupiter, bright and undeniable. Unlike Borisov, it refused to drift, its trajectory nearly gravitationally perfect. The chemistry was stranger still. Nickel without iron, a spectral signature no local comet had ever produced. 3 interstellar visitors, 3 different patterns, none obeying the rules. If a textbook definition of comet had ever existed, Atlas was tearing it apart. For scientists, these contradictions were both exhilarating and unnerving. Each new anomaly eroded confidence in the old models. It was as if nature, or something beyond it, was reminding us that the category of interstellar object might hold more variety than the solar system could ever prepare us for. If Oumuamua, Borisov, and Atlas were all members of the same class, then that class was far broader and stranger than anyone had imagined. As Atlas crept closer to perihelion, the debate shifted from classification to implication. What message was hidden in its motion, its slow drift, its impossible chemistry, its surge in brightness? Each carried information, even if no words or signals accompanied them. If traditional SETI had trained us to listen for radio beacons, Atlas reminded us that not all messages come as sound. Some arrive as presence, as mass and motion, as objects that refuse to fit categories. The comet was not speaking in a language of code, but in the grammar of anomalies. It was slowing when it should have sped up. It was glowing green when chemistry said it should not. It was shedding nickel without iron, drifting as if immune to its own tail. Each fact alone could have been dismissed. Together they became a statement that no one could ignore.